Ah, that blue icon. Is it 23rd? Ballpark? Cool. Okay, so two things I want you to get out of this chapter is knowing what a determinant is and how to calculate it. And how to calculate it. Okay, so for 2 by 2, first of all, the determinant can only be calculated for square matrices. And if it's a 2 by 2 matrix, that's going to take two-dimensional input shapes into two-dimensional output shapes. The area is going to change, and the determinant measures the area expansion factor. If the determinant is 2, the area of the output shape is 2 times the area of the input shape. It's a 3 by 3 matrix. It's taking three-dimensional input shapes to three-dimensional output shapes. If the determinant is 2, then the volume of the output shape is 2 times the volume of the input shape. And that goes for higher dimensions. Okay, and then how to calculate a determinant. And so I'm going to show you 3 different ways. So last lecture, we did elementary row operations. I'm going to show you the cofactor expansion right now. And then there's shortcut rules for 2 by 2 matrices and 3 by 3 matrices. The 2 by 2 is just AD minus BC. And a mathematician named Saras, who I've never heard of except in this context, came up with a nice way to calculate 3 by 3 determinants. Oh, it's the Jacobian in Calc 3 is really a determinant. So one place where you're going to see determinants in an upcoming class. They won't have the language of linear algebra for it, but essentially, it's when you run into the Jacobian, you're going to be using determinants. What's it? What's it? Saras. I think it's 2 R's. Yeah, it looks weird. Yeah, it might even be 1R. I think it's actually 1R. Exactly. So whenever you're doing a cofactor expansion, you'll have to pull up the appropriate sized checkerboard matrix. And it's just a matrix of positives and negatives. And here's our problem. Okay, so to find a cofactor expansion, you have to pick a row or a column in the matrix. So any preference here? First or second? First, row or column? Sounds good. And we'll do another one. So I just want to show you it always ends up being the same thing. So here's our matrix. And you said first column. So that's what I'm going to look at. And let me move this down here a little bit. I put the checkerboard underneath. So it's that first column here. So I get +1 -3. So I'm using the first column entries as coefficients, and whether I keep them or change their sign according to the checkerboard. And then what I like to do is put a copy of the matrix up here. I've got the 1. I cross out 1's row and 1's column and put the remaining number here. For the 3, cross out 3's row and 3's column, put the remaining number there. For -6, the determinant is -2.
Is this like an expanded version of what you do with your cross product?
Yeah, we'll be essentially, I'll show you how to do what's essentially the cross product calculation with a 3x3 matrix. Yeah, so yeah, this is the 2x2 version of that process. Let's try it again. But you can't say first column. So I want to emphasize you can pick any row and any column. So first or second. Okay, I'll go second, row or column. I'll say row. But you could have picked anything here. Original matrix. Checkerboard. We're doing second row. So it's -3 +4. Okay. We cross out 3's row and 3's column. Take what's left. 4's row and 4's column. Take what's left. We've got -6 plus 4. The determinant is -2. Okay, let me show you how this works for the 3x3 case. And you can do a cofactor expansion along any row or any column. Yeah, so I'm going to do, that's a good choice. So when you're doing that cross product calculation and also the three-dimensional curl, you'll be doing this cofactor expansion along the first row. But it really works anywhere. And this is the matrix we looked at last time. Okay, so set up the checkerboard. We're doing first row. So this is going to be +4 times something, -5 times something, +6 times something. Okay, I cross out 4's row and 4's column. And I copy that 2x2 matrix into the slot. Cross out 5's column and 5's row. Copy that into the slot. Cross out 6's row and 6's column. Copy that into the slot. Okay, then I'm going to do the 2x2 determinant here. And I'll use the shortcut rule, but you can do it however you want. 4 times 10 minus 6 times 8. Two times 10 minus 6 times 7. 6. 2 times 8 minus 4 times 7. 40 minus 48 is -8. 20 minus 42 is -22. And 16 minus 28 is -12. So that's 104. As we calculated last lecture with the elementary row operations, this determinant is 6. Okay, I think, do you want to see this determinant calculated along a different row or another column? First column? So do you want to see one more? Or okay, yeah, so let me And column 1. Okay, so take the matrix. Put the checkerboard under it. And then here, cross out 2 rows, 2, 5, 6, 8, 10, 7, 7, 5, 6, 4, 6. Now it's the 2 by 2 determinants, 4 times 10, 6 times 8. And so that's 4. 40 minus 48 is -8. 50 minus 48 is 2. 30 minus 24 is 16. Let's see what, let's see, 6 times 7 is 42.
It's 7 times 6.
7 times 6, you're right. -42 minus 4 is 38. Oops. Oh yeah, that is 6, as expected.
Unknown caller.
Okay, let me show you the 3 by 3, the 2 by 2 shortcut rule we just used here. So Saurus's rule. Shortcut for 3 by 3.
Unknown caller.
So same matrix, a little bit bigger. So what I'm going to do is take the matrix, grab the first 2 columns, and copy them again over here. Make 2 copies of this. So it's kind of similar to the crisscross in the 2 by 2. I'm going to do some forward. 4 times 4 times 10, which is 160. 5 times 6 times 7, which is 210. And here I've got 6 times 2 times 8, which is 96. And those all get pluses. And then I do 3 backwards. 1, 2, 3. 6 times 4 times 7. 24, 140, that's 168. 4 times 6 times 8. 6 times 8 is 48, 96, 180, 192. And that third one, 5 times 2 times 10 is 100. These are all negative. If I do 160 plus 210 plus 96 minus 168 minus 192 minus 100, the answer should be that 6. That's all there is to it. So just, you got the 3 columns, put the first 2 columns after that, do the 3 forward diagonals, the 3 backwards diagonals, and forward is positive, backwards is negative, and put them together. Okay, so it's more time than I wanted to spend on determinants. Is chapter 7 and 8 are where the class starts getting very interesting. Oops, I'm gonna need my notes for this. Okay, so first, a warm up for the intro. So if I take 20 and increase it by 10%, what do I get? 22. Increasing 300 by 10%. 330. So the calculation you're making here is you've got your 20, and then you do the 10% of 20, which is 20 plus 2, which is 22. 300 plus 10% of 300, 300 with 30 added to it, you get 330. So if I want to increase just some number x by 10%, I start with x and I add 10% of that. And then I can factor an x out of this and get 1.10x. So to increase x by 10%, you multiply x by 1.10x. So if I start with x and multiply it by 1.20, that's x increased by what percentage? 20%. You got it. If I want to decrease 20 by 10%, that's 20 minus 2. That would be 18. Or if I want to decrease 300 by 10%, 300 minus 30 is 270. And in general, if I want to decrease x by 10%, I take x, subtract 10% off. I can do the same trick as before So another way to say it is decreasing X by 10% is just take 90% of X. So if you saw an expression like this is X decreased by how much? 30%. Good. So what's going to happen down the road is I'm going to see an expression like this, and I really want you to see this as this is X increased by 10%. Okay, so I want you to imagine we're in the American Southwest, and we've got a bunch of road runners and a bunch of coyotes. Right? So road runners try to escape from coyotes. Coyotes eat the road runners. Okay, what's going to happen if we have a large roadrunner population? Now, let's see. If we have a lot of roadrunners, there'll be a lot of new roadrunners made, but also there will be a lot of, so the roadrunner population will go up, and there will be a lot of coyotes, or there'll be a lot of food for the coyotes, so the coyote population should go up. And if we have a large coyote population, well, then the roadrunner population will start going down because they're going to be eaten. And there's not enough food for all the coyotes, so the coyote population will go down as well. So we're going to keep track of these. C of t is going to be the coyote population in year t. And R of t is the roadrunner population in year t. And so what we want to look at is next year's coyote population and next year's roadrunner population. Okay, so the number of coyotes next year is going to depend on how many coyotes there are this year. It's going to be essentially how much competition there is for food. And it's going to depend on how many roadrunners there are. The more roadrunners we have this year, the more coyotes we're going to have next year. And the more coyotes we have, the more that's going to decrease next year's roadrunner population. And the more roadrunners we have this year, then we're going to have, that's going to add to next year's roadrunner population. So the thing I want to point out here is if C is 0, then the only thing that matters is next year's roadrunner population is 14% of this year's. So no coyotes. It's the roadrunner population is going to increase by 14%. It looks very linear algebra like. Okay, we have to keep track of two things. We can do it with a vector. So we're just going to think of a two-dimensional vector where the x-coordinate is how many coyotes we have, and the y-coordinate is how many roadrunners. And we can vectorize this whole thing. So next year's population vector And we can look at this as a matrix. What? Oh, thanks for telling me. Did it just show up? Okay. That's where, yeah, it usually happens right at the beginning. Thanks. Let me know if it pops up. So what this matrix does is it transforms this year's population vector into next year's population vector. So we call this the transformation matrix. So you see what it does is I start with this year's population vector, apply this matrix to it. It's going to transform it into next year's population matrix. Okay, so there's going to be a couple special ratios I want to look at. So one of them is when the coyote to roadrunner ratio is 1:3. So example. So either 100 coyotes to 300 roadrunners or 50 coyotes, 150 roadrunners. So let's look at this one. Okay, so this year we have 100 coyotes and 300 roadrunners. The next year, we apply this matrix to this input. And it turns out I'll spare you having to do the arithmetic yourself. It's 110 and 330. So what I want you to notice here is that both populations increased by 10%. And that's going to happen with any population vector that's in this ratio of 1:3. So if it was, what do we have? 2,000, 6,000. Also, both populations increase by 10%. Let's make that a little bit nicer. And there's another special ratio. So that's when the coyote to roadrunner ratio is 2-1. So here, this seems reasonable. There's a lot more roadrunners than coyotes. So there's a lot of roadrunners around to make more roadrunners. They would be increasing at 14% if the coyotes weren't there, but they still get an increase of 10%. And the coyotes have a lot of roadrunner food, so there's population to go up as well. This seems like both would decrease. There's a lot more coyotes than roadrunners, so the roadrunner population isn't going to increase, and the coyotes are going to be competing for food. You get the idea. So let's take this one. So let's do the transition matrix. Apply it to this. I just want to emphasize here, we're doing that calculation we've been doing all semester. Let's make this a little bit nicer. So both populations decreased by 10%. Okay, and that's those special ratios are rare. So let me just show you. You know what happens if it's not in one of the two special ratios. So imagine it's 100-100 this year. And then next year, and I worked this out for you, it's 94-102. Okay, so here, is the populations had different relative changes. So first special, the 1-to-3 ratio both increased by 10%, 2-to-1 ratio both decreased by 10%. But here, the relative changes are different. So okay, but this is where it gets interesting. I can break up that 100-100 as the sum of two different vectors. This down here. So this first vector, the Coyote to Roadrunner ratio is 1:3. That's one of the special ratios. And here, this Coyote to Roadrunner ratio is 2:1. Okay. So when I've got that 1:3 ratio, each population increases by 10%. And when I have that 2:1 ratio, each decreases by 10%. So next year's population is 94,102. So I want to look at our 100, 100. And watch what happens year after year after year. So next year, year after that, year after that, year after that. So. Write it this way. I think I'll have enough room here. Okay, so I'm going to split it up into the 20/60 and 80/40. And then as we go to year one, it's the 20/60 part increases by 10%, and the 80/40 part decreases. And then as I go into year two, this increases by 10% again. That decreases by 10% again. And as I go into year three, and year four, okay, I want to say a little bit about what's happening here. So if I take 90% of 90% of 90%, if I take the limit as t goes to infinity of 0.9 to the t, what's that number? Yeah, that's 0, right? So as t approaches infinity, this part actually approaches okay, so we can say long term, the population approaches a ratio of 3 coyotes, 3 roadrunners, for every coyote, and both populations increase at a rate of 10% per year. So I'm going to start giving you some. No, let's do it. No, we'll do it this way. So in the 1-to-3 ratios, actually, let me go back to the examples I actually used. So, so say that a vector is in the 1-to-3 ratio just means it's some multiple of the vector 1, 3. And vectors in the 2-to-1 ratio that's 100 times 2, 1, 3,000 times 2, 1. And then when we split our 100, 100 as 2 vectors, so we did is we wrote 100, 100 as a linear combination of these 2 vectors that represent each of the special ratios. So really the right basis for this, or right basis for this scenario is we'll use B. I'm going to give you some vocabulary. Eigen is the key prefix here. So the basis that represents the special ratios is called an eigenbasis. Vectors in the special ratios are called eigenvectors. So, so anything that's a multiple of one of these eigenbasis vectors is called an eigenvector. Okay, then, so this is the Greek letter lambda. Okay. When the coyote to roadrunner ratio is 1:3, we know each population increases by 10%. So in other words, if we start with this year's population, scale it by 1.10, this is called an eigenvalue. And traditionally, we use the Greek letter lambda to stand for an eigenvalue. Okay, and when the coyote to roadrunner population is 2:1, so if I've got 200, 100 this year, multiply, so to decrease each by 10% is to take 90% of it. So that relative change is called an eigenvalue. Okay, so let me say use all these words in a way that's similar to how we're going to be using them. So if I take my transition matrix, so this is how we're going to say. So we're given a matrix, and then the eigenvector represents a special ratio where both components change by the same relative amount. So the factor that represents the relative change is the eigenvalue, and then we have corresponding eigenvector. And when I'm lecturing, I'm going to abbreviate this. Just write lambda is the eigenvalue, and then I'll write the eigenvector underneath it. And then also lambda equals 0.90. It's an eigenvalue with corresponding eigenvector to 1. And not surprisingly, the way I'm going to write that and then a basis made out of eigenvector is called an eigenbasis. Yeah, so let's do it this way. Okay, so this year, my population vector is 100, 100. And then remember what I did earlier. As I said, I can break that P into 2060 plus 8040. So another way to say that is the coordinates of P relative to the basis B are 2040. Okay, then I said for next year, I take representation. Let's give myself a little more room here. Okay, so this is the calculation I make. Or oh, actually, let me do it this way. So this is 110 times 20 times the 1, 2, 0.90 times the 40. That's 1 to 3. Goes to 1. Okay, or another way to say it is, now this is the 20 increased, so write it this way. Next year's population vector relative to B is 2236. So let's write it this way. So if I decide just to work in this new basis, I see that the x coordinate increased by 10% and the y coordinate decreased by 10%. So if I want to do this with a matrix, so my 2040 input goes to 2236. And the right way to look at this is 1.10 times the 20 plus 0 times the 40. We're doing this in chapter 2. So the matrix that turns this year's population vector written relative to the eigenbasis into next year's population vector written relative to the eigenbasis, that first row is 1.10, 0. And second one, this 36, is I don't use the 20 at all, and I take 90% of the 40, so we've got the 0.90. So let me draw a picture of what's happening. Give you a moment to get that in your notes. I want to draw a picture of what's happening here. And the matrix that does that is the one I can never remember. .86, 0.08, negative 0.12, 1.4. And if we want to do that transformation relative to this better basis, that's the transition matrix. So we've got a matrix that's transforming input vectors into output vectors. The matrix we use depends on the coordinate system we're using to represent those input and output vectors. In the original system, number of coyotes, number of roadrunners, it's this transition matrix. But those special ratios give us a better basis where the transition matrix is nicer. I'll write it down here. So as we do the calculation from this year to next year, we can either we start here and we end here. We can either do it directly with the given transition matrix, or we can write it as a three-step process. So just names. This is often called the matrix A. It's just given. D for diagonal. Okay, and then remember our eigenbasis is 1 to 3, 2 to 1. This is the B to S matrix, and P inverse is the S to B matrix. So as I do step 1, step 2, and step 3, step 1 is convert S coordinates to B coordinates. That's P inverse. Step 2 is to use the diagonal matrix to turn this year's population vector into next year's population vector relative to B. Step 3 is to go back, and that's going to be the same result as doing A. So I'm going to leave this. We talked about factorizations in chapter 5. This is a factorization of A. Okay, so that's an overview of what we're doing. Actually, let me tell you one last thing. So what we want to do is, given a matrix, find eigenvalues and eigenvectors. Well, actually, just to find eigenvectors. So the matrix of the transformation relative to the new basis is diagonal. This is the easiest matrix to work with, and we want to find the correct basis. So working relative to that basis gives us a diagonal matrix. So that's our main goal. And then starting next week, I'll talk about how to do the actual calculations. Okay, so you're officially excused. You want to hang out and talk a bit? I'm good with that. Zoom linear algebra. I'll send this to the morning class. And I will send this to the evening class. Yeah, take care. What's that?
See you next week.
Yep, see you next week. Have a good weekend.
Practically over the summer. Could we request back to all the-
That I have no idea about. There's people who know that. I just,
Extra. Oh, thanks.
say it again.
I hate this class.
Then take it.
Oh, right on. You do the delta function? Yeah. What's this? Oh, you're on an A. Well, that's something. Yeah. Yeah, just 5 minutes. Yeah. It's funny because there's this one guy. Selling. It's not his big organization. So one of my clients, one of my clients, yes. Sees me grab stuff and go outside. Yeah. No, no. And like I was saying, if you ever, you were so you're completely. Yeah. It's Oh, so- Yeah.
now, right?
Yeah, it's supposed to be. Okay.
These bathrooms don't have it posted.
Okay. Talk to you, right?
No, I'm gonna give you one of these. Oh, you already have it? Okay, yeah, because a lot of you don't realize the bathroom coordinates with whatever rooms across the room. So this one is bathroom, it would be 239.
Okay, cool. Thank you.
Do you need to move? Yeah.
We don't have that much material left. Earlier, I was worried we were gonna run out of time before material. I think it's gonna go the other way.
If you're on this, where do you like the reports? It's totally
What is it?
the lectures report.
They're there. The recordings or the,
The recording.
yeah, let me show you.
Because yesterday I was trying to go to week 6. There is no, after week 5, there is no.
Yeah, let me show you.
Okay.
Okay, so I got a little bit confused here.
Mm.
So in the modules, um, I first started putting the lectures up here in the modules.
Yeah.
And then I ran out of space. And it's like, asked them for more space, they gave me a little bit more, and then I ran out again. So let's see, videos for lectures on or after February 24th are here.
Okay.
So I had to switch mid-semester. And then here's all the lectures from end of February.
So I go to the modules and the link.
Right.
Video, lecture. Thank you.
So they're there. It's, as always, first time you teach a class, there's always share my screen. And usual, we get a blank notebook here. Today. Actually use a lot of these, but I just put in a bunch of the functions that we had before. Question? Yeah, good question. The worst part is I did not save this last night. It's even worse. Yeah, let me do this. Let me type it in again, and then I'll put it as an announcement on disaster. That was supposed to save as something that apparently it didn't. Old stuff. Okay, so this is what I'm going to type in. We've talked about these in earlier lectures, so let me go to Canvas.
Yeah, define a function is easy to put. Something new.
Canvas. Put this in the cell to give you a moment. Isn't they just opened a blank notebook? Yeah, they had a bunch of pre-written functions here that I put in as an announcement. They're just going to Canvas. Look at the announcement. Okay, so
so just as you're getting this in an overview of what these functions are, we talked about standard units. So that's a nice way to measure everything in terms of the mean and the standard deviation. The correlation is the R value. Positive R means that there's a positive association between X and Y. Negative R is a negative association. The value is always between -1 and 1. It's how well a linear predictor is going to do. So how linear, it's a measure of how linear the data is. R equals 0, there's no association. R equals 1, it's a line. Draw a line is not interesting. We talked about how to find the equation of the regression line. So the regression line is the best linear predictor. Today's lecture, I'll quantify exactly what I mean by best linear predictor. And this is how we calculate the slope and the intercept. So the slope is the correlation coefficient, the R, times the standard deviation Y divided by standard deviation X. And there's the formula for the intercept. One, draw a line function. And let me drop things on the graph. What's that? Yeah, I'll put together my cheat sheet, and of course, you're gonna put yours together as well. So it'll either be on yours or mine. So, for one thing I like about this class is we get real data. We looked at this table last time. So this is every congressional district in the United States, by state, which district it is, median income, what percentage of people voted for Hillary Clinton, and what percentage of the population has a college degree. And what I want to focus on is just the relationship between the percentage of the population that has a college degree and the median income. We've got all the data there, but we want to do some interesting data science with it. I'm going to do drop some columns. I'll drop the state column. I'll drop district column. And I'll drop the two things that I'm interested in now are what percentage of the population has a college degree and the median income. Draw a picture of it. So it looks like it's a positive association as the percentage of college degrees increases, the median income tends to increase. We want to measure how linear that is. So maybe if you go from take the correlation. So it's fairly tightly correlated. 0.81. One would be a perfect linear relationship. 0 would be no relationship. Somewhere the closer it is to 1, the tighter the relationship. Trends as the college percentage goes up, the median income. So now let's try to get that linear predictor. So we want a function, a linear function that gives us a best estimate for the median income based on the college percentage. We did call that the regression line. For your algebra class, a linear function can be written as y equals mx plus b. That's the slope. M's the slope, b is the intercept. And set up formulas here, table in X and Y, graphics table, percentage. In last lecture, we talked about how to do this calculation. So roughly what this predicts is if 0% of the population had a college education, so nobody had a college education, we would expect the median income to be $20,802. And that as you increase the college percentage by 1, that median income would go up by $1,270. It's predicted 10% had a college education, their median income would be this base value plus 10 times. Let's draw the scatter diagram again. And along with regression line. Looks like we got there is our regression line. Looks reasonable to me. Of all the possible straight lines I could draw, that does seem like a good one. So this part of the lecture, I want to focus on how good the fit is. That wasn't a perfect predictor. Sometimes it was, but for the most part, it hit some of the dots. You know, that one was pretty good. That one's close. Here, at 70, we would have predicted a median income up here. We actually got something. So we're going to define the error error to be the actual value minus the predicted value. Seems like a reasonable way. There's different ways I can define error. And notice error could be positive or negative. Positive error means the actual value is above the predicted value. In other words, the prediction is underestimated the actual value. Negative error, the predicted value is too high, the predicted value overestimated. Error.
So it is reverse, when it is positive, over, and negative.
Yeah, so yeah, it's probably best if I do this with an example. So imagine the actual is 8. The predicted is 10. The error would be -2, smaller than 0, and that means the predicted overestimated the actual. Prediction is the same thing here. The actual is 8, and the prediction was 6. The error would be positive. That would be an underestimate. The nice thing about defining having signed error, error can be positive or negative. You not only know the magnitude of the error, how far off it is, but in which direction.
Would be using correlation? This defining how much an error.
Yeah, they're related. So we're going to do it just straight up for any predictor, what the errors are. So possible linear, or how bad the error could be. What we're going to do though is talk about the error for any predictor. So you give me a linear predictor, and I will calculate the error for that. And we'll see that correlation, we can use the correlation coefficient to build the best possible linear predictor is the one that minimizes the error. I think that these. Vocabulary word we'll be talking about a little bit later in this lecture. Next lecture is sometimes we call the error the residual. I always think I prepare these. Nice. using the y equals mx plus b here. I'm using the y equals mx plus b. My x coordinates are the college percentage, and then I'm plugging that number into the y equals mx plus b formula to get the predicted y. Here are the errors. Interesting. What I did is I made a table, or I added to the table what the predicted errors. I did this before, I can't remember the context. So what we want to do is come up with a single number that tells us how bad the prediction was, or how good. So for each possible data point, we've got a prediction, we've got the actual values, we have an error, and we want to talk about a single number that measures the total error. Surprisingly, no, and watch why. Yeah, that's the point I'm going to make. Is that average doesn't do it.
It's different.
So watch this. Is the average error is going to be close enough. Yeah, so what, because you have some positive errors and some negative errors. When you add those together, they're going to cancel each other. So it's, yeah, this is a good point. So this is an interesting question that people talk about a lot. It's called the L1 error. In machine learning, this is often much, there's mathematical reasons that I'll talk about. Something slightly different. But this is, I think, the obvious way. Actually, I'm kind of curious about this. Let's do some. Here's the L1 error.
Then you divide it by.
Right, and because you'd always be dividing by that, you could do anything. Either divide by how many there are. Or so what I'm imagining is we've got exactly the same data, and we're using different predictors, and we want to pick the one that has the most error. So if we divide them all by 100, it would be the same number.
Oh.
But you're right, like when we did standard deviation, we divided by it. Sometimes here.
Yeah.
How far it would be. want to get here. What we're going to use is what's called the L2. It's also called the root mean square.
Oh,
The rough, I guess here's the rough idea. So if we just had two data points, is you think about these two numbers as forming a vector, 3 units in the x, 1 in the y. And your prediction is another point in the xy plane. And then the error is the length of this vector. And the way you figure out the length of this vector is Pythagoras. So this is the idea we're going to use.
that's like standard deviation.
Yes, very simple.
Is it the proof?
Yeah, exactly. Yeah, you just divide by n. Exactly the same way. This is how we're, can you see that?
Yeah.
Okay. And let me know if this is the one we use. And it's really because we're computing distances. I'm going to do it by hand in some sense. Three minus two is one of the errors. Like this. So 3 minus 2 is the first error. 1 minus 4 is the second error. What I'm going to do is square each of these. Then I'm going to take the average and then take the square root. So I'll write this out in 3 steps. Calculate the errors, square every error, add them up, divide by how many we have, and then take the square root of that. And here's the step-by-step process. Here's the error squared.
One error method better than that.
Yeah, it depends on 2 things. I guess several things. One is kind of what you're optimizing for. So is the L2 error penalizes outliers. So because of the squaring, this is going to minimize really big errors.
Oh,
Right. So everything's going to have an error. So the L2 error is, yeah, I guess for an error you can look at the maximum. So you get a linear predictor that minimizes the L1 error. You got a linear predictor that minimizes the L2 error. The L2 predictor is going to have fewer places where the L1 error, there might be a couple places where the predictor is away. The L2 error punishes those.
Is it kind of like median versus median? Where depending on, because like for median, it doesn't consider as much of the like
Yeah, so yeah,
extremes.
right, yeah, so yes, the outliers don't really affect.
Affected, but then with the mean, it affects it a lot.
It's
So
similar.
depending on what you're,
Yeah, it's very similar.
yeah.
You know, it's,
Like that's kind of like the house price thing, where it's like if you look at the house prices in the area, if you want to know kind of like an average,
oh,
if
right,
you take an actual average,
it's terrible.
it's terrible because there's so many. I mean,
Oh,
not so
okay.
many, but there are houses that are like really,
Yeah.
really expensive. That skews it.
Right.
So to have a more realistic idea of what most people are paying, it would be better to take a median.
Absolutely right.
So then that's kind of like. if
Yeah,
you're-
similar, yeah, so it's, yeah, how much the outliers. affect.
But yeah.
So this is kind of what I exaggerated. It's the L1 might have one or two places with a huge error and others that are fairly close. L2 is most likely to have not any individual errors that big, but there's more smaller. And that's because the squaring is 19 squared. Oh, so 19. Remember, you're going to square the errors here. So if you're 7, it gets squared, it turns into 49. We had a 19 down here, it would turn into 49. But then the other is with machine learning, you're really trying to minimize an error, and you have to worry about computational costs. So even though mathematically the L2 error is nicer, L1 is just much faster to calculate. Spend your computing power doing something else instead of. This class is going to be L2 error. Sometimes.
Just to like make sure that L2 is for when you're expecting that the data doesn't have a huge disparity in prediction.
It's what you want to do is your best linear predictor is the one that has the smallest possible error. And how you've got different ways to define error. You can define an L1 error or an L2 error. So those
Yeah.
are going to give you different reasons.
Yeah.
And finally, the root squared error, which is the L2 error, is let you take a minute to absorb it, but that's the step-by-step process. Do a particular numeric example. Here's the actual value, here's the predicted value, the error is actual minus predicted. Then what we do, square the errors, add them up, divide by that 1, 2, 3, 4 data points, and then we take the square root of that. Take the errors, square them, sum the squares, divide by the number that we have, and make the square root. If you like math notation, that would be great. And then you can also do it for 1 line. Just done one single line. Here we squared the errors. The mean does the average, adds them all up, and divides by the length, and then to the 0.5 is the square root. I just wanted you to see once exactly what we're talking about. What's that?
We're gonna make a function of it.
Funny you should mention that. Say that again?
The average of the sum of the you just want to like write it out. Then we just want to show it.
Exactly. Yeah. So essentially, I'm trying to write this formula in step by step. And the second one is exactly the same calculation, which is done every single time. It's the mean, the square root of the mean of the squares of the errors.
Okay, so basically, multiply by itself.
Yes. Yes. at your suggestion, put this into a function. RMSE is of course. I'm gonna say 1200. So let's say I wanted my regression line to be 1200x plus 21,000. There's the root square error. When I use the regression slope and the regression intercept, I get a smaller. And the theory, this is something you'll learn in the linear algebra course. Oh yeah, it's linear algebra or calculus 3 is, this is the best we're going to do. The regression line is the line that minimizes the L2. Let me show you something cool about Python. So, hold that thought. What I've done, see this table I made. What's the smallest output? Smallest Y value? Tell me what I did. So you see what I did. So the Y value is X value minus 2 squared plus 3. And I see on the table that the smallest Y value is 3, and the input that produces that is 2. And you kind of see that here is this expression is either 0 or a positive number. We're going to get the minimum value when we make this 0. The minimum value is 50x. So now, I'm just going to make that function x minus 2 squared plus 3 and watch what Python. Two decimal places. Only to minimize, Python minimize function, this function that you found here, actually finds the input that produces the smallest output. So now there's a Python function that will take your function as input and tell you what input you should use to produce the smallest possible.
But I thought it was zero.
Oh,
Or no,
So when this expression is zero, we get the smallest point. And
oh,
the
but then
x
y equals, wait,
So the x value that makes this part equal to zero
Is
is
two.
x equals two.
oh, yeah, okay, yeah.
So putting this together is we have a new way to calculate the regression. You know, the regression line minimizes the root mean square error. And we have a Python function here that will minimize any function. So here's our function. Python to minimize that for us. And that was a function that took two numbers as an input. So these are the two numbers we use as input. Here are that. Regression line slope. Or close enough, pretty much nailed it. So we had the equation for the regression line, but we basically had a formula for the slope, r times standard deviation of the y minus standard deviation. The intercept is some synthetic function. But now the Python minimize function, as long as we can quantify the error, will give us the regression. Here are a couple of cool things we can do with this table. Actually, yeah, let's back up a minute, an overview of what we've done. We're in the predicting part of data science. Exploration, prediction. And so far we have two strategies to make a prediction. One is just, you've got the data, you've got an unknown input, you want to find predict what the output would be, is just find some points in the data set that are close to the input point you're looking at, and then use the data you have to predict the output. And we're going to talk a bit more about that in the next section. Okay, second is if it looks like the data is linear, if the R value is close to 1 or close to -1, we can use a linear prediction. And we've got a formula for the equation of that linear. We also see that Python has a way of minimizing a given function. So if we can write a function that will tell us the error for any possible linear predictor, Python will tell us the slope of the intercept of the best. Two different ways to get that.
And the best one is.
Yes. Important witness. And the best one is the regression. So you have two different ways to get the regression line, either from the formula or from using Python to minimize the error. Let's just go through one more and get the linear regression. Data. It's this, I think. They took a bunch of athletes and they did the training with the athletes. measured what their maximum amount of weight they could lift. So I think one day they just said, we're gonna do a power lift the largest possible weight we can. They recorded that data. And then they also, in the meet or in practice, saw how far they could throw a shot. Roughly, you think the stronger they are, the stronger they are, that would be evidenced by the amount of weight they could lift, which would also translate into how far they can throw. But there's numbers. Let's take a look. I must put a zero there. It look like a positive association. That's good. Take a look. Table. What's that shot? Okay, yeah, pretty close. Let's find the regression line. It'll be exactly the same calculation. Graphics. This time. Shot. It's calling the minimize function is going to give me an array with the two inputs I need to minimize it. And then that first number is the slope of my regression line. The second number is the intercept. So again, first out of the list. Now, let's draw this pattern diagram with the actual regression line. Looks like we want to go from about 25. Yeah, looks pretty good. Now we can objectively measure how good it is. Because there's the root mean square. Any linear predictor that you gave me would have either matched the root mean square error if you gave me the regression line, or would have had a higher. Then this is
Wait, can you repeat what that number means? That's the
that was-
root mean square of root of the regression line, slope and intercept.
So the regression line is determined by the and that predictor. And so you've got the actual values, and then your predictor predicts some values. So if you calculate the errors, square the errors, and do this, you do this with the errors, that's what that number is.
That's the L2 error.
Yes.
And then, so that tells you how good your prediction is.
Yes.
But then what, and that is like above or below zero thing?
No.
Wait,
This is always going to be positive.
positive, okay.
So
So then it's like the higher the number, the worse it is.
yes. So if we have a perfect predictor, the predicted value is always the actual value, right? The errors would be zero. Yeah, figure this one. So now this was a study that somebody published, and then somebody. Say that again? No, I'm sorry. Error. Yeah. RMSE is root mean square error. So this is a debate the data scientists will have. Is what is the best formula type for the predictor? So maybe a quadratic predictor, a parabola, would fit the data better. Two data scientists arguing. So you want a simple formula that makes the prediction. Oh, remember our model here is observed data is the real data plus some noise. So if we're trying to predict the children's height based on the parents' height, the height of the parents got to eat as they were growing. Less food means they're going to be shorter. So then we've got the arguments about what formula generates the underlying data. We've been assuming it's all a linear predictor and R measures how good, but there could be an argument. Maybe this is better predicted by a function of this formula. So the linear algebra course, just like we learned the formula for M and B, you would learn a way to mathematically define to figure out A, B, C. But luckily in this class we have access to Python, and we can do the same thing. We can write our error function and then use the Python minimize function to figure out A. All right. I might do this during lab time. I think what I want to do in lab time is get the L2 error and the L1, or sorry, the best L1 predictor, linear predictor, and the best L2 linear predictor. do pretty much the same code. Except we're going to be doing our predictions. We want our prediction to have three parameters. So if we ax squared plus bx. Okay. Our prediction. I'm going to show you this.
So this is assuming a different kind of correlation. right?
Yes.
Like at a certain point, it's gonna start going.
Or up, yeah.
Or up, yeah, sorry.
Yeah, you're
Well,
absolutely
what
right.
kind of data would that? Like, like something like age?
Yeah, good
It's
question.
hard to kind of just visualize,
Imagine.
or like,
But then, let me think through it. There's got to be quadratic models of population growth.
because I can see, yeah,
Oh, maybe a population.
yeah,
That would actually be more exponential. But yeah, so it's a population.
right?
So an ideal population.
But then exponential is kind of,
And you can do an exponential regression as well.
yeah, but that's different than quadratic.
But so if this would be what the model would predict. Imagine that if I actually take the population data year by year. Yeah. It would look like this. So as a linear predictor, would just be a line like that. And a quadratic predictor, at least, would probably more closely fit.
So a little bit speed, when the, how speed the relation, how X affect Y in the speed of time.
Yeah.
When
Yeah,
the
so
time
yeah,
is constant, then it will be a line. When it is changing its speed, it will go up, down.
Yeah, I agree. I'm going to just reword what you just said. So in a linear prediction, it's no matter where we are, when we increase X by a certain amount, Y increases. So is we can imagine that Y is increasing with X at a constant rate. But it's possible that Y might be increasing with X at an increasing rate. And so that would be better modeled by a quadratic predictor than a linear. So I still owe you an actual real world explanation, but that's the idea. So what's going to happen when I call minimize? That's going to give us three numbers. And so here's one line Python code where I can just extract those three numbers out. I remember when I had two numbers, I did it kind of a funky way. It's I called the minimize function, I called item 0 and item 1 to extract the two numbers. Here, there's something called a tuple. No, I think I got this here. Yeah, drop and rattle up. Just so you can see what this looks like. Zero. So I want to go from 20 to 140. I don't know if it's a better predictor or not. Okay, so two things I want to do is next lecture, we're going to picture the errors or the residuals. What we hope is that there's no pattern to the residuals, the linear fit was good. If there's some pattern we see, we can see some weaknesses of our linear predictor. And then the last thing we want to do in this unit with linear predictors is instead of just predicting one number, we want to predict an interval and a confidence interval. So we want to say that the predicted number, we're 95% sure that the predicted number is going to be between two. Oh no, so the actual, we're 95% sure that the actual number is going to be between 10 and 12. So instead of saying here's the prediction, we want to say more with the confidence interval. We want to say how sure we are. We want to give a range of numbers it could possibly be, and how likely it is that the predicted value will be. That's Monday's lecture next week. And then we're going to go that idea of calculating the child's height based on the average of the parent's height. We're going to take that idea with different cases. Lab time. No. You know what it's going to be. I'm going to take a break. You can take a break or not. I'll be back. Carrie will be here. Ari will be here.